So hopefully you're as excited as I am to get to learning what the heck a Turing machine is, and how does it work, and just taking a look at these machines that are as powerful as the machines on our desks. And what I'm going to do in this video is a little bit different than most of the rest of the class. Normally, I introduce the way that the textbook approaches a machine like a DFA or an NFA or a PDA first, and then I say, oh, by the way, here's how it works in JFLAP. Because Turing machines are not really any harder, but much harder to simulate a run on, we're going to start with JFLAP, because if we look at Turing machines in JFLAP, then it'll be really much easier for me to show you what's going on in the machine. And then at the very end, I will talk to you about how our textbook talks about Turing machines, and it's almost the same. The setup that I've got for you in JFLAP is almost identical to the setup that the book has. So here's a kind of cartoon drawing of a Turing machine. In fact, there are a bunch of different models that you can have for a Turing machine. This is just one way you can think of a Turing machine. You can think of it a bunch of different ways, but this is the way that we're going to do it for this class. Okay, so a Turing machine kind of has an NFA inside of it. That's the CPU. So inside of there's some circles and arrows that are hidden in there. Okay. It's a little bit different from an NFA, a little bit different than a PDA, but we'll get there. And instead of having a stack for our memory like we have in a PDA, now we get an infinitely long piece of tape, we call it, right? An infinitely long piece of paper that has a bunch of cells. So here's, there's one cell and there's another cell, and we can write one thing in each of these cells. Okay, and each Turing machine instruction, which is in the CPU, is going to tell us when you can run that instruction, right? Based on what's the current state, right? What circle am I in right now, and what symbol am I pointing to by the tape head? So it's just like the way we did it with a PDA, where we said what's at the top of my stack and what letter do I see? Well, now we're going to kind of do something very similar and say, what is my tape head, right? This arrow out of the CPU pointing at, right? And it's also going to tell us what to do, how to run the instruction, right? What should we write on the tape? How should we move the tape head? And how do we transition to our next circle, our next state in here? Now, even though we are starting with JFLAP this time, I am setting up my JFLAP Turing machines so that they follow along with the kind of Turing machine that we have in the book. So in addition to all this stuff I already talked about, the Turing machines in our books have a single special state inside the CPU, right? One of these circles that is called the halt state, and there's only one of them. And when you get to the halt state, you stop processing and you accept the string. No matter whether you've processed the whole string or not, the whole string gets accepted if you get to the halt state, and you just stop. All done. Okay, so welcome to Dr. K's attempt at making you slow down and look at this slide. This is super important, what I'm about to tell you, and I figured if I had penguins with guitars, you might pay more attention and say, what was that penguin with guitar thing? So what I want to tell you is, in order to get your Turing machines to work the way mine are working, and in order to do all the work for the rest of the Turing machine section of this class, you have to do some setup in JFLAP that is super important. So when you open up JFLAP, where can I put this so I don't show off, I don't hide all the penguins, because they're cute, right? And by the way, here is my my citation for where I got the penguin images from, because we always cite our sources, right? So when you get to JFLAP, before you tell it that you want to make a new Turing machine, and I'll tell you about that in a minute, you're going to go to the Preferences menu. Now, I have already set mine up, but under preferences, you're going to go to Turing Machine preferences. And what you want to make sure that this enable transitions from Turing Machine final states is not checked. So this better be unchecked. You want to have accept by final state checked, right? So, oops, I just unchecked it, but I could go back into preferences and check it again, right? And if we go back into preferences, look, it's checked. Accept by halting is not checked. I know I talk about halt, but don't say accept by halting, please. This is a different halt from the book, so just ignore that for now, okay? But make sure it's not checked. And say you do want to have checked allow stay for tape head on transition, okay? So you absolutely need that set up. Here again is another slide with more penguins, just to show you exactly what you need, okay? You need these guys checked off, these guys blank. Okay, these guys checked off, these guys blanked. If you don't do this, so many things are going to mess up. So I figured it was important to show you here. Okay, so not quite as important as with penguins, but still big. When you pick, when you're going to make a new Turing machine, we're always going to just use this Turing machine with building blocks option. So let's start by having a Turing machine over the alphabet A, B that halts at B, okay? So what we're effectively doing is we are having a Turing machine that accepts any string of A's and B's that, that has a B in it, right? And it can have as many A's in it as it wants, but as soon as it sees a B, because halt means stop, you're done, it accepts, even if there's more B's and A's afterwards. So let's just jump in and I'll show you. So here's my, my JFLAP tool, and let's pick a Turing machine with building blocks, and we get a screen that looks kind of like this. Well, no, actually it looks exactly like this, and let me just make it a bit bigger, and we'll make the automaton size a little bit bigger here so you can see what's going on. So it feels an awful lot like NFAs and PDAs. I'm going to make two states. The first state, I am going to make an initial state, right? I clicked on the attribute editor. This last state, I'm going to make a double circle state, a final state. But again, as you remember, I said we only ever have in our book approach to Turing machines a single state called halt. And so what we're going to do is we're going to not have this called Q1, but just to remind ourselves that the accept state is halt, I'm going to right click on this state and I'm going to say set name. And so instead of calling it Q1, I'm going to call it halt. Okay. Doesn't really change anything about what's going to happen here, but what it does do is it reminds you, let me just make this a little bit bigger. It reminds you that this is the halt state. And when it gets to the halt state, that's just different than a regular old accept state. Okay. So what I'm going to do is I'm going to put two transitions on here. Let me just show you. So I picked the transition creator, and I'm going to just click on Q0 so I get a loop. And it gives me 3 spots here. And what I'm going to say is, if you see an A on the tape, then what I want you to do is replace it with an A. In other words, don't change it, and move the tape head to the right. So that's what this R means. I actually have a choice of go right, go left, or stay put. Okay. Oops, I hit enter, but that didn't do diddly squat. I'm going to click now, and then it'll make it go into a loop. Okay. So there's my first transition, AA, and go right. I don't expect that this is going to make any sense yet, but as soon as I show you a couple of examples of it running, you will immediately understand what's going on. Okay. So here's my transition creator again. And yeah, we got some weird stuff up. Just ignore it. Just ignore it. We're not going to look at that right now. I just took the normal transition creator, and now I'm going to go from Q0 to halt. And if I see a B, I'm hitting tab, then I'm going to write a B, and maybe I'll stay put. I'm going to type a capital S. I could also use the drop-down menu to pick the S, but you can also just type, and then I'll click outside of there. And here's my machine. So just like with any other kind of JFLAP machine, you can just use the input menu to do step, We're not going to step by building block, just step. Okay. And let's start with the string AAAB. Okay. And here we go. I hope you can see this. This is big enough. What I'm going to do is I'm at Q0, right? I start at Q0, and you can see the machine is at Q0. It tells me I'm at Q0, and it has a little arrow here, which is the tape head, right? And the tape head is currently pointing at an A, because whenever we use a Turing machine, this is a JFLAP standard, and it's also the textbook standard. It always starts you at the first letter in your string. Okay, so we're going to start at this A, and we see an A. So what we're going to do is we see an A, we're going to replace it with an A. In other words, don't change it. Just erase the A and write an A back there, and then move the tape head one space to the right. So I'm going to say step. And now you can say, now, because remember this is an infinite tape, right? Infinitely long. So it looked like the tape moved to the left, but in fact the tape head moved to the right, right? They're the same thing, relativity and all that. So now we're pointing at this. We see an A. So we see an A, we write an A, and we're going to move the tape head to the right. So moving tape head to the right, we're going to point at that A next, right? Step. Oh, look, we see an A. We see an A, we write an A, we move the tape head to the right. So we step. Aha, we see a B. Can't take this loop anymore. We're going to take the B, we're going to replace it with a B, and we're going to stay put, but we're transitioning to halt. So watch what happens. I take the step, and instantly this turns green. My string was accepted, right? So that's very nice. Seems to work well. Let me just try it on another string now. I'm going to shrink the size of my machine slightly so that I can maybe show you it a little bit more close up. Let's try this on the string AABBA. Okay. Now we start out exactly the same way as we did before, right? And if you think about what would happen with a normal, like if this were an NFA or a PDA, getting to an accept state doesn't mean you stop. It just means that you check and see whether your string is empty. And if your string is empty, you just have lambda left over, right? You've processed the whole string, then you're good, then you can accept. But remember, on this machine, we accept the whole thing. Anything that's written on the tape gets a thumbs up as soon as we get to halt. So let's see what happens. We take a step, and we're going to take that loop and stay at Q0, take the loop and stay at Q0. Now, of course, we're going to take this transition. So I'm going to take one step, and green, we're done. Halt, right? We are done, right? I can't take any more steps. If I click on step, nothing happens, right? It goes away. It cannot step anymore, right? We are done. We accept. So this machine accepted AABBA, right? So what is this machine going to accept? It's going to accept anything that starts with 0 or more A's, has one B, it has to have a B, right? And then it can have as many A's and B's afterwards as it likes, as long as we're restricting it to the alphabet A, B. Of course, we could, if we increased our alphabet, we could have whatever we wanted after the halt, right? After it reached the halt, at the end of the string, after the B. So the language that this machine accepts over the alphabet AB is 0 more A's, followed by a single B, and then as many A's and B's as we want, right? So this machine is a machine that recognizes or accepts this language, even though sometimes it stops before it gets to the end of the string on the tape. So let's just go back and review what I said Turing machines do, and we're going to look at it in the context of JFLAP, right? And so if the current state of the machine is I, right, you're at this state, and you see an A on the tape, then you're going to replace that A with a B. Of course, these could be the same things. And move the tape head the direction D by one cell and go to state J, right? And the directions can be go left one cell, go right one cell, or just stay put, don't move. And as I said before, just because we want to be consistent with the Hein textbook, we're going to have one final state. We're going to call that halt. And because we want to be consistent with Hein, we're going to stop and accept immediately when you get to, well, I say any final state here, right? But we've set that up in our system so that in JFLAP, right, by doing the special settings with the penguins, right, it stops and accepts immediately whenever you get to any final state. And that's equivalent to the textbook talking about stopping at a halt state. And yes, this is different than JFLAP's talking about stop on halt. So ignore what JFLAP's setting said and just follow this. So again, as a reminder, this state right here that we had in our Turing machine is just a normal final state. We called it halt to match the book approach, right? We just changed the name of the state to be halt. It was Q1, we changed it to halt. We made it an accept state. Since our settings are set to accept by final state, this works like the textbook's version of halt. Okay. So let's just talk about all of the assumptions that we're making for Turing machines. These come out of the book. The input string is written on the tape, and all the other tape cells contain, in the book they talk about lambda, in JFLAP they think of it as a blank, but same thing, right? We know lambda is the empty string. The tape head starts at the leftmost symbol of the input string. I said this before. There's only one start state, of course, as always. The textbook says there's only one halt state, right? So we're going to stick with that. If your machine gets super, super messy, you can make another state called halt 2 or something, and we'll just pretend they're the same so you don't have to have crisscrossing wires. The Turing machine stops if there's no valid move, or if it arrives at the halt state. If it stops and arrives at the halt state, then you accept it. If it stops somewhere else, then you reject it. We haven't seen an example of rejection yet, but we'll get to one, don't worry. Okay, so let's do another version of the same kind of machine. I just want to show you a little bit different kind of a Turing machine. Okay, so let's take this machine that we already have, and let me just show you, oh, this is the simulation, sorry, that's why, here we go. I just wanted to use the selector and highlight these and move it over. There we go. What I want to show you is that this machine really will stop and accept at halt no matter what. So let's just add one more state in there. And let's put one more transition in here that says if you see another B, then replace it with a B and go right. Okay? So theoretically, if you look at this machine I've got here for a minute, if it sees a B, it writes a B and stays put. So it's guaranteed to see a B when it gets here, right? Because it was still looking at this B that it wrote. Okay? So this is my machine. Let me shrink it ever so slightly. Let me move this down so that, so that when I do the trace, I can show you the biggest window possible in your video. Okay, so let's just run this, let's step again, right? Oops. Oh no, it says there's transitions from final states. Please remove them or change the preferences in the preferences menu in the JFLAP main menu. Whoa, okay, never mind, because we have the, selected in the JFLAP main menu. Remember, let me just say File, New, and you can see the preferences again. And we said, we didn't say enable transitions from Turing machine final states. So since we didn't say that, it's not even going to let me do this. I'm just not going to show you what happens because it doesn't let me do it. Let's go on to the next example. Okay, so here's our next example. I want to show you how to do a Turing machine that actually does accept A star B. So that stops at the B and doesn't let you have anything after the B, right? And what we're going to need to know is that the JFLAP uses sort of this blank square as the equivalent of the textbook's lambda. So let me show you how to build this machine. Here's our old machine. Let me just say File, New, and we're going to do a Turing machine with building blocks. Remember, that's the one we always pick because that's the one that we will want to use sometime. And here it is. And what I'm going to do is I am going to make a couple of states. Let's make, oops, let's pick the state creator. Let's make 1, 2, 3 states for this one. This first state, I'm going into the attribute editor, and the first state is going to be my initial state. This Q2 here is going to be my final state, but because I like to remember that that's actually halt, I'm going to right click in the attribute editor and say set name, and we'll call the name halt again. Okay. Let me squish these a little bit closer together so you can see what's going on. A little bit better, make it a little bit bigger. Okay, so what I'm going to do is, just like before, I'm going to have a loop on Q0 that accepts as many A's as I want. So I'm going to click once on Q0, and you see there's that little square there that looks like the square up here. That's going to be useful for us in a minute. So I'm going to say, if you read an A, I typed an A, you can't see it. I don't know why we can't see it, but anyway, then write an A and go right. So there's our, maybe this automaton is a little bit too small, or I moved it a little bit too far over. Let's pull it this way a little bit. Okay, so there's my, if you see an A, write an A and go right. And then we're also going to put in that same transition we had before from Q0 to Q1. Well, this used to be our transition from Q0 to the halt, but now I'm going to do it to Q1. What I'm going to say is if you see a B, right, and I'll click here, that space goes away, write a B and go right. Okay, so we leave the B alone. But now what we're going to do is we're going to see after you've gone right from that B. Now before we stayed put, right, this time I'm going to go right. After you've gone right, if the string is in the language A star B, then we should just see a lambda after that, right? A blank space on our screen. So what I'm going to do is I'm going to do another transition, and this is going to be the transition that takes me to halt. And I'm going to hit tab, and you'll see if I hit tab, the space appears, right? So if I hit tab, it's kind of the default for these first two slots in a JFLAP Turing machine is to have spaces in there, and when we click, we overwrite that space and put something else. But what I'm going to say is if you see a space, then leave the space alone and let's stay put. And so here's my transition. Straighten that out. Oops. Here we go. Isn't that prettier? So what do? We see for all the A's, we replace them with A's and go right. Whenever we see a B, we replace it with a B and go right. But when we see a space, we replace it with a space. We stay put. We go immediately to the halt state. Oh, by the way, this is not whenever I see a B, right? This is I see one B, I go to state Q1, I'm done with my B's, right? Then if I see a space at Q1 and not some other junk, I'll keep going, I'll stay put up, but I'll keep going to the halt state and then I'll accept. So let's do a couple of examples with this. I want to squish it down a little bit so that when I run this, you can see it better. All right. So let's try and test some strings on this. Let's start by testing 3 A's and a B again. Okay, so A, B. And let's see what happens. We have 3 A's and a B, and notice the tape head is at the very first letter in our string. And if I say step, it takes that loop, sees the A, replaces it with an A, goes right. I see that state, it goes right again, right? Does the same thing. Tape head is now over an A, it'll do the same thing, stay at Q0, right? Still telling us at Q0. Now it sees the B. This loop isn't going to work anymore, so it's going to take the B, see the B, write the B, and go right. We're going to end up at Q1. Step. Now we're at state Q1. What do we see? We see a space, right? Just a blank space on our tape. Remember, this is an infinitely long tape, so there's an infinite number of blank spaces at this end and an infinite number of blank spaces at the other end, but we see one of them. We see a space, we're going to replace it with a space, we're going to stay put, we're going to go to the next state, right, which is halt, and now we accept, right? So the string A, was in our language, right? Now let's try, let me close this, and let's just try another example of a string that has junk after the B, and I'll just show you how it's not in the language. Okay, so I'm going to do input step, and let's try AABA. Okay. And let's see what happens. We start on A, we see an A, we write an A, we go right, step. We see an A, we write an A and go right, step. Okay, now we see the B, so we're going to transition to Q1. And look, we're at Q1. Now we see an A. And now we're going to kind of fall off this machine the way we fall off the NFAs and DFAs, or PDAs for that matter. There's nowhere we can go. We are not at halt. So when I say step again, oop, did you see that? Sorry, that was too fast. When I said step again, couldn't do anything, so it went red. Let me reset and let's just try it again. So we do step, step, step. We now see the A. I'm going to say step, but it can't do anything. So now I have to say step one more time, and it turns red to show me it didn't accept it. Okay. All right. So this particular Turing machine we just looked at only halts with success on A star B and otherwise fails. So now that you've seen a couple examples, let me just show you the difference between what the textbook says and what's in JFLAP. Right, so, you know, if I'm trying to make these look exactly as closely as possible, so, you know, we might have a label I on this state equivalent to this one, label J on this state equivalent to this one. And in the textbook, we just use sort of a different fraction notation. So if we see an A, then we replace it with a B and go right. If we see an A, replace it with a B and go right. That's what it looks like in JFLAP. You know, in the book, really, it's usually in black and white. Looks more like this. In JFLAP, we usually use Q0 and Q1 as states, but, you know, same kind of thing. In the textbook, boy, I made that blue. Really, of course, it's just a circle with an H around it. In JFLAP, a double circle would serve as halt if we're doing JFLAP, if we're using the JFLAP settings that we've set up. For purposes of my class, I like to write halt in a double circle. I think it's clearer. But really, textbook and JFLAP, super close. Okay, so now let's talk about something called determinism. You know about deterministic finite automata versus non-deterministic finite automata, and deterministic PDAs versus non-deterministic PDAs. Now let's talk about deterministic Turing machines. So if a Turing machine has at least two instructions with the same state and input letter, which, you know, we can also call the same weather conditions, the same conditions that tell you how you can move, then it's non-deterministic. Otherwise, otherwise, it is deterministic. This is so similar to what we did with PDAs. With PDA, you had to look at what's the letter and what do I see on the stack. Right here, and what state am I in? Here, it's what state am I in and what's the letter that I see on the tape. And that's it. So let's look at an example of a non-deterministic Turing machine for A star B plus A star BC. We could do this machine in a deterministic manner too, but I just wanted to show you a relatively simple non-deterministic Turing machine example, and this seemed like a good one to pick. So let me just show you my machine now. Remember that with a non-deterministic Turing machine, there's nothing that says you have to have blank spaces in it. Nothing that says you have to have lambdas. I happen to, but there's nothing about lambdas in here. So let's just take a look at this. This machine is going to accept A star B or A star BC, right? All of the strings in this language. So if you have a bunch of A's, followed by a B and a C, you're going to go this path, and then you'll see, remember, we have to have that lambda at the end so that you know that that's the only string you've seen, and we go to the halt. If we see a bunch of A's and then a B, then we also halt. So it's going to accept that language. And notice that when you're at Q0, if your tape head is over the letter B, then you have two choices of where to go, right? If you're Q0 and you see a B, well, you could choose to go this way. Or if you're at Q0 and you see a B, you could choose to go this way. So let's just test this machine out. Here's one I made earlier. And let's see what happens. If I say input, let's step, let's pick the string. What did I say? It's A star B plus A star BC. So let's just pick AAAB. Okay. So we are at state Q0 and we see an A. So we take that loop. We've been doing this for a while. At Q0, see A, take that loop, A, Q0, see A. Remember, it's C and A, right and A, go right. Now we see the B. So we're at Q0 right now, and we see a B. And of course, as we know, there's two possible ways to go. Let's see what happens when I say step. Well, when I say step, JFLAP, brilliantly, says, well, maybe I'm at Q3, and I'm looking at this because I had to go right. Or maybe I'm at Q1 and I'm looking at this because I had to go right. Both times I'm looking at lambda, right? I'm looking at an empty square. Let's see what happens. Well, if I'm at Q3 and I see an empty square, I'm gonna stop here, right? It's not gonna work. If I'm at Q1 and I see an empty square, it's gonna let me go to the halt, right? So let's do a step. And what happens here? Q3 fails, but this path got to the halt. So yay, I accept, because there is a path that leads me to halt. That's all I need, a path that leads me to halt, and I accept this Turing machine. This string on the Turing machine. Let's try another example. Step. And this time, let's just try something that's not in the string. Let's try, it's A star B plus A star BC. Let's try ABB and see what we get. So we see the A. Of course, I don't need any A's, but whatever. We see the A. I do the loop, step. We see the B. Now we've got the choice, step. We've got the two situations. We see the next B. Everybody fails. We're done. Not accepted. Right? Let's do one more. Actually, let me just show you can also do multiple run, right? And these are leftovers from a different example that I did. So let's try what happens if I put a B by itself. What happens if I put AB? What happens if I put BC, right? Because it's A star BC, so, or A star B. What happens if I put, I don't know, AAAB and AAABC, and let's try some AAABB or BCC, and let's just run the inputs, and look, accepts because that's in the language, A star B, accepts because that's in the language, A star B, right? BC, that's in my language. 3 A's and a B, sure, that's in A star B. 3 A's and a BC, yup, that's in my language. 3 A's and a BB, nope. A B and a CC, nope. So far, whenever we see a Turing machine step, we always have replaced a letter with the same letter. Here's a different example. I'm going to actually, I'm saying cross out A's, but what I'm really doing is just whenever I see an A, I'm replacing it with an X. So here's my Turing machine, and you can look here. If I see a B, this is over the alphabet A, B, C, by the way. If you see a B, I just replace it with a B. If you see a C, I replace it with a C. But if whenever I see an A, I replace it with an X, right? And I'm going to loop all the way around and keep doing this until I see a lambda, right? Until I see an empty space on the stack. At which point, sorry, did I just say on the stack? On the tape, right? My infinite tape. And then I'm going to, if I see a space, I'm going to write a space, and I'm going to stay put, and I'm going to go to halt, right? I'm just going to go to the end. Okay, so let's do a couple of examples here. Let's try it with, I don't know, click, A, B, A, B, B, C, 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 B, A, B, C. That looks like fun. Okay. So what happens? I'm at Q0 and I see an A. Well, if I see an A, I need to replace it with an X and then go right. So when I step, look at that. It's now an X. Amazing, huh? You impressed? I have a B here. Well, with a B, I just replace it with a B and go, right? Ooh, another A. So we're going to replace it with an X. Another A, click. Another A, click. Another B, another B, another C. C we just leave alone as well. Step. Another C, step. Another C, step. Now we have a B. We don't do anything with that. Oh, an A. We're going to replace it with an X. And then we have a B, so we leave it alone. And we have a C, so we leave it alone. We can't even see our tape is so long. We can't see the left side here. But now we're at a blank. So we're going to go to halt, step, and we accept. So now we have not only accepted, but we've accepted and we've, changed what was on our tape. Very exciting. And you can simulate this with a bunch of examples. Let's do a multiple run again, and let me make this a bit bigger so you can see what's going on here. And let's see, these are all over the language ABC, so that's okay. Of course, if we put something in here that's a different letter, right? So if I put AAABDBA, right? We expect that's going to freeze up. We can, of course, also enter lambda, right? Because lambda should get accepted by this, and just not do anything to it. Let's just try one more. I've started with a lot of these. Let's see, B, 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 C, C, B, C. What happens if there's no A's? Well, it's just going to do what you expect. All right, let's run the inputs. Yeah, so it's told us that this D got, this string with the D got rejected. All it's told us here is all of these strings have been accepted. That's not really all that interesting to me. But what we can do is you can click on one of these guys, like, so let's click on AB, and let's say view trace. And you can't actually see it, but it pops up with the final state. Sorry, you couldn't see it because it was off the screen, right? So I brought it here. What it does is it pops up with the final view of the tape, and you can see it's turned it into an XB. It stopped there at halt, right? Or we could view a trace of this one that got rejected. And let me just drag it down. And you can see we have XXX, right? Because we had those first three A's. And then B, and then the D it halted at, so it didn't even X out that last A because it never got there. It halted, it was done. Okay, so what we're going to do now is we're going to modify our Turing machine so that after it crosses out all those A's and B's, it's going to go back to the start of the string, right? So now it's going to replace all the A's with X's, and then it's going to move left until the tape head is pointing at the first character in the string, all right? We're going to use a special symbol for this. It's essentially a bang, right? A not, an exclamation point that goes in front of a blank space, which means anything but blank, right? Not works for other things too. To do a not blank, we're just going to type not and it'll work. We're also going to use tilde, which sort of means the last thing that you saw. It's a little bit weird. You can use it sparingly. I think I found a bug in tilde, and I've sent in a bug report, so we'll see if they have time to fix it or not. It was in a particularly specific weird case, so tilde mostly appears to work, and we're going to use it in this example just so that you can see how we do this. So you can use tilde. If you're using a tilde and something is super wrong or something is going weird, just be prepared to say, maybe it's buggy, right? And try and do it without a tilde. Okay, so let me show you this. So here's what we had before. What I'm going to do is I am going to get rid of this transition. And I'm going to scooch, oops, I had them both selected. Sorry, I'm going to scooch halt over here. And I'm going to add another state in there. And what I'm going to do is I am going to say, okay, as soon as you see a space, so you've made all your changes and you see a space, go to Q1 instead of to halt. So let's make a transition. We're going to say if you see a space, leave it as a space, but now go left. Go back into your string, right? Let's pull this over just a little bit. Okay. And now, as long as you see something that's not a space, you're going to go left. We'll see an example. If it's not making sense what I'm doing, it'll make sense. So what I want to say is, if I don't see a space, and if I don't put anything there, then it just leaves it as a space, right? So what you have to do is you just have to type just an exclamation point and nothing else and hit tab. And it says just exclamation point here. After we finish, it'll label it correctly. But if all you see is anything but a space, then replace that with whatever it was that you just saw. So now we're going to say replace it with, and I'm going to use that tilde that I said sometimes is dangerous. And then what I want you to do is go left. So let's look at this transition. As long as you see something that's not a space, this tilde essentially means leave it alone, write back what you saw, and move left. And we're going to keep going left until you run out of characters on your string. And then if we see a space, then leave it as a space and go right and halt. So let's run this machine and see what happens. Let's do a step and let's try to run it on, I don't know, CC, oops, it's not typing, CC, A, B, C, A, C, B, A, okay. All right, so we started the C, and we're going to start with what we were doing before, moving along to the right and Xing out all those A's. So I'm going to do this relatively quickly, step, step, step. You can, of course, try this too. If you're in my class, I'm going to make these machines available. If you're not in my class, I will try to make the machines available. Okay, so here is the, here's this blank, right? So we are in Q0, we see a blank. We're going to have to jump to Q1 and go left, right? If you see a blank, leave it blank, go left. Okay. So now I was at this blank, but I've gone left and I see this X, but I'm now at state Q1, right? Tells me that. And Q1 says if you see anything that's not a blank, leave it alone and go left. So I see an X, I'm going to leave it alone and go left. I see a B, I'm going to write that B back because that's what this tilde means, whatever you just saw, and go left. And I'm going to keep doing that. There's a C. It's not a space, so we leave it alone. We write the same thing back and we go left. We see a C. Leave it alone. We go left. Ha ha. I am now at the space on the left side of my string. That matches this space. It doesn't match this not space. So we're going to have to take this transition. If I see a space, leave it alone and go right and then halt. So now we have changed all the A's to X's and gone back to the start of our string. Okay, so suppose now somebody asks us to make a Turing machine that crosses out all the A's, capitalizes all the B's, and then goes to the start. Now, it would be pretty easy to change this Turing machine we just made so that it would do that, right? I mean, all we need to do is delete this one transition, right? So we could delete this one transition. Let's just do it. We'll delete that one. And then we will add a new transition where we say, if you see a lowercase b, turn it into a capital B and then go right, right? And that gets added here. And this will work, and you can test it and say, boy, look at that. Isn't it great? It works. But what I actually want to do is I want to do something a little bit different. I want to show you, basically, I want an excuse for using a building block, and I'm going to use this as a building block. Building blocks are essentially functions, and it would be really nice and make your Turing machine code look much cleaner when they get bigger if you could use, you could build Turing machines out of other smaller pieces of Turing machines. So what I'm going to do is I'm going to undo the change we made. So I'm going to click undo, and notice when I click undo, you don't say anything, see anything, but then if I click in the window, it sort of fixes what happened. So let's try it again. Click undo, click in the window. There we go. Now we got to click undo, click in the window. So now we're back to what we had before. And I'm going to save this window. And now I'm going to point out that I called this example 6 crossout, and it says, oh, cross out A's, then go to the start.jff, right? So that's what this thing is saved as. Save it one more time. And now I'm going to do a new Turing machine with building blocks, and that popped up way over there. I'm going to take this guy and close it. And so what I'm going to do now is I'm going to show you how to use this exciting building block creator. And what happens, I don't know if you saw that. Let me cancel and do it again. I clicked on the building block creator. I clicked where I wanted to put the new building block. And then I can choose, what do I want to do? What do I want to put in there? And in fact, I want to put in there this example 6, cross out the A's, and then go to the start. Oops, I clicked again. Let's cancel. And so here is this thing that looks just like a regular state, but in fact, if we go to the attribute editor, I can right click on it and say edit block, and it shows me everything that's inside that block. Okay, and let's close the edit block out. And what I'm going to do is I'm going to use this first one to cross out all the A's, and it goes back to the start, right? And then I'm going to use another one of these. Let's use another building block creator. And I'm going to stick another one of these guys in there. Okay, which is the cancel. Sorry, I clicked again without going to the attribute editor. Don't do that. Okay, so I went to the attribute editor, and so now I have 2 of these blocks, and right now they look exactly the same. If I right click and then say edit block, I can look inside. And what I actually want to do is I want to change this second block. So this second block, I guess if it sees an X, I'm going to leave it alone. And if it sees a B, I'm going to change it into a capital B. So let's get the transition creator, and I'm going to say, if you see an X, just leave it alone and go right. But if you see a B, turn it into a capital B and go right. And I'm going to leave the rest of our machine exactly as it was. And now I will close the block. And this does not change the original file. And if I go over here, yay, I'm in attribute editor, and I right click and I click on edit block. This one still has turned the A into X. But if I close that and I go here and I right click and I say edit block, this one is how we change it. So when it makes the copy, it makes it makes a brand new copy that you can edit and do whatever you want with. So if I close that edit block now I have these 2 things here. And the question is, how do you connect them, and how does that connection work? So the first thing I'm going to tell you is you can connect these with all sorts of things. If you want, you can add transitions, sorry, you can add states before and have transitions to them, and you could have, like, I could make, oops, I'm not very good today at not clicking the attribute editor. You can, I could right click this and make this the initial state, and then I could have some sort of a transition from this initial state to there. I'm going to hit escape because I don't really want to do this. I'm going to get rid of that state. But you can also have these states be the start state. So I'm going to do that. I'm going to make it the initial state. So what I'm going to do is I'm going to go into my program and immediately do this. And then the way that these building blocks work is when the machine stops. Now the JFLAP documentation says when the machine halts. What I'm going to say is, since your textbook uses halt as halt and accept, we're going to say when the machine stops, either because you have halted and accepted, or because the machine has failed, and that's important, then it starts looking for an out transition to see where it goes next. So what I'm going to do is I'm going to stick in an out transition like this, and I'm going to say, okay, once you've stopped, when it's stopped, we expect that it's going to be at the first character in whatever our string is, which is going to be either an A or a, no, sorry, it's not going to be an A, right? It's going to be either a capital X or a B or a C, right? And one thing that we could conceivably do here is we could turn this into a as long as it's not blank, which is what we sort of expect is going to happen, right? Then, oops, let me get rid of that and try again. We could say, as long as it's not blank, so I'm going to hit an exclamation point. In that case, leave whatever was there. Remember our tilde? And I'm going to say stay put. Okay. And if I do that, and then let's add a halt state for this machine. So I'm going to take Q2. I'm going to change the name. I'll call it halt. Oops, let's make it all capitals. That's what we've been doing, right? And I will make it a final state. And, you know, I think what I'm going to do is I am going to change the name of this because this is really long. I'm going to just call this one, instead of this long thing, I'm going to say Crossout A's. And we'll remember it's go back to start after it's done. You can't really read it because of this, but anyway. And then I'm going to rename this one, and we'll call this capitalized B's. I'll just call it cap B's. Okay. All right, that's a little bit better. So now I can make these a little bit closer, and I can move my halt up here. And now we will do another transition that's exactly the same again, right? As long as we see anything that's not a space, so I just hit the exclamation point, then replace it with whatever was there, tilde, right? And stay put. And if we test this machine, we'll see that it mostly works. And I'll show you the problem in a minute. So let's suppose that we do step. You can do step by building block, or you can do step. Let's try step by building block first. And let's try with A, B, B, C, C, A, B, A. All right. And so when I do a step, it's going to do everything that has to do in that first building block. So you can see it changed all the A's to X's and came back to the start. And next time I do a step, it's going to do all the stuff in this building block. And now we're at the end, and now I'm at halt, and it accepted. So we're in good shape. So that's kind of what we expected. And in fact, if I click on this and say trace, I'll bring this down here just so that you can see that it did indeed take our, we had A, B, B, C, C, A, B, A, and now it's X, 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 cap, cap, C, C, X, cap, B again, X, right? So it looks like it worked, right? That's great. And you can also, let's close this, you can also just do a regular step. And when you do a regular step, it shows you everything that's happening, but it doesn't actually give you like a vision into the internal. So let's do something small here. Let's just do B, A, C, okay? So as I do the steps, it does everything inside of those building blocks, but it doesn't actually show me what's going on, right? Or it shows me here. It says, oh, look, you're in state Q0. Well, great. I don't remember what state Q0 is. And I can't like right click here. The only thing I can do is say display state labels. That's not really very helpful. So I can keep stepping, right? Step, step, goes back. Look at that. I have a capital B now. It goes back to the beginning. So now we're done with this one, and we've jumped to halt according to this. And now that we're at halt, it accepts. So that all looks great. The trouble is, what happens when we do something that has a letter that's not in our language, and we've used these kinds of transitions? The important thing is we've just said, as long as it's not a space, keep going. Okay. So let's try one more. We'll do a regular step so you can see kind of what's going on. And let's try the string A, C, B, D, A. Okay. So let's say okay. And we start at A, and I'm going to do a step. It crosses it out. That's what we expected, and we're at, you know, in here somewhere. And we do another step, right? We're still at the Q0. Remember the loop guy. I don't think I can click on the editor now. No. All right. So we do another step, and everything's looking good. We've, you know, left the C alone. We've leave the B alone because we're in that cross out A's phase. Now we see the D. When I do a step, it stops, right? It falls off the machine. Right? Because if we just look at what's in there, here's the the old example 6 Turing machine, it saw the D and none of these worked, and this didn't work, so it stopped. It fell off, right? In JFLAP terms, it halted, but so it left this and it looked for transitions that it could take out, and it said, oh, look, I'm on a D. I can't do any of these loops, right? I've frozen, I'm done. So I'm going to take this transition out, okay? And I'm going to keep going. By the way, I think I said this already, but if it halts at a halt, that's fine too. It just starts looking for transitions. It doesn't, a halt inside one of these building blocks doesn't behave the way a halt outside does. It just is another way to stop and leave the building block. So now it's gone to the cap B's and we're pointing at the D, right? So if I say step again, well, it was in that same loop thing, right? The loop looked a little bit different, right? Because we had, this is a B and a capital B in that second one, but still it's going to look at this stuff and it's going to say, well, I don't have a B, I don't have a C, I don't have, this was a capital X in the other one, right? So, and I can't take this jump, so it leaves. And then look what happens to us. It leaves, it goes to halt. This is the real halt at the top level, and so it stops, and boy, our string looks nasty. So that was the what not to do. So let's get rid of this, and let's get rid of these two transitions. So you need to think a little bit harder about what happens when you leave. What happens if the machine freezes? What are the possible states it could freeze in? And under what circumstances do I want to keep going, right? So in this particular case, it seems to me that we want to make the transition from this first state to the second state if either we see an X, right? So if we see an X, we'll just leave the X alone and we'll stay put. Or if we see a B, we'll leave the B alone and we'll stay put. Or if we see a C, we'll leave the C alone and we'll stay put, right? Because if I bring back my original machine again, after we've gone left, right, we go right and we go to the beginning of the string. And at the beginning of the string, after we're done, when we get to this point in the Crossout A's code, it's going to either have X's, C's, or B's on the tape if stuff is going well, right? So that's what we're going to do to transition here. By the time we finish up in here, if all is well, we're going to potentially have a capital B that it's looking at, right? Because it moves back to the first letter in the string. So let's do some transitions here. So it could be an X, in which case leave it as an X and stay put. Or it could be, in this case, a capital B, leave it as a capital P and stay put. That was capital B, by the way. Or it could be our lowercase c, in which we leave that there and we stay put. So now let's do a couple of tests here, okay? Let's do a step and let's try one that worked before and make sure it still works. So let's try, well, something like one that worked before. C, B, A, B, A, C, C, B. Okay. And if we just step through this, I'm not going to narrate the whole thing, but you'll watch what happens. We're going to move to the right. Maybe I will narrate the whole thing. And we'll change those A's to X's as we go, right? And when we see that space, we start moving left. And then after we see the space, inside of our building block, it says go right, and then it goes to the halt, which means that it jumps to the next, it leaves this, it looks for something like this. Look, it's pointing at a C. It has a C, so now it should go over to the cap B. And now it's at the cap B, right? And now it's going to go inside the cap B, and we step, and it stays at Q0, and notice how it's capitalizing the B's as we go. And then it goes all the way back to the left until it sees a space, and then it sees a C. And so now it's at the halt inside of that machine. And now we're going to jump out here, and it should, because it sees a C, follow this guy and go to our real halt, and life is good. If we try simulating, let's just try simulating something small. Let's do one more step where we say, what happens if I have A, D, B, C?
So we start and we are in this one and crossing out the A's, and we step and we get to the D, and it's going to freeze right inside of that machine. It can't do anything with the D. So it's going to look and see, can I move along here? And it can't move along there, so it fails, which is exactly what we want to happen if we have a D in our string. So couple things I want to remind you or tell you about building blocks. First off, for the purposes of our class, you can use building blocks because you could do essentially the same thing with a raw Turing machine, but it will make your code look a lot cleaner when things get complicated. You may not use this tool here. This is Block Transition Creator. You can look it up in the JFLAP tutorial if you want. It lets you do some interesting jumps here that are more or less like this, but there's ways to use it that lead you to more bad code, let's say. So if you're not careful. So I'm just going to say you can use the building blocks, but you can't use this block transition creator, but you can do what we just did and use the regular transition creator. And that makes things a lot easier. Okay, so let's keep going.
Okay, so the next Turing machine I'm going to show you is one that adds 1 to a binary number. This, of course, requires that you remember binary numbers and you remember how to add 1 to a binary number, all these good things. So let's start with just a super quick review, right? So the binary numbers, if we have our decimal numbers, are 1, 2, 3, 4, right? Maybe we'll even put in, for excitement, 5 and 6. In binary, that's 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, right? And you remember, of course, you remember that the first digit here represents the ones digit. This represents, or actually, I suppose I could write it in, right? So this first digit here is the 2 to the 0 power digit, right, which is 1. The second digit here is the 2 to the first power digit, which is 2. And the third digit is the 2 squared, or the 4 digits. So you can see that 4 plus 2 equals 6. 4 plus 1 equals 5. This is 2, right, because it's the second digit. So 2 plus 1 is 3, and so on. So you all remember your binary numbers, right? And so what we want to do is to just add 1 to each of these numbers, right? Make sure we remember how to add 1 to a binary number. So sometimes it's super easy, like if we say, what is 1, 0, 0 plus 1 in binary? We say, well, 0 plus 1 is 1, and 0 and nothing is 0, and 1 and nothing is 1, and we're good. If we have to do a carry, it's ever so slightly harder, right? 1 plus 1, well, 1 plus 1 is 2 base 10, which is 1, 0. So 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, and then we're just going to copy the rest of that, right? Oops, 1, 0, 1, 1, right? That should be a 1. There we go. And what about if we add 1, 1, 1 plus 1? Well, 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And there we've got our 0, our 1, right? What is this in real life? It's 4, 5, 6, 7 plus 1 is 8. And yeah, that's the 2 cubed position, so it's looking good. I think I have 1. Yeah, there we go. One last one. So we've got 1 plus 1 is 0, carry the 1. And now you notice I'm going to just keep doing this carry until I get to that 0. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. Ah, we've got a 0. 1 plus 0 is 1. And then there's my number.
So let's talk about how a Turing machine might add 1 to a binary number. Here's kind of my algorithm. I'm going to start by moving to the right of my string, all the way to the right, and just make sure I just have ones and zeros until I see a lambda, an empty space, right? And then once I see that, the end of the string, I'm going to move left by one cell. And then remember what we did to do the math, right? If I had a 1, I had to replace it with a 0 and carry the 1, but that's effectively just moving left, right? And I'm going to keep writing a 0 wherever I see a 1 until either I've run out of digits in my string, in which case I carried the 1 all the way past the end of the string, or I see a 0, in which case I can replace it with a 1. And then I'm just going to move to the very start of my string and stop. So here's my Turing machine that adds 1 to a binary number. And I've kind of got the algorithm here on the left so you can see it. So I can remind you my algorithm. Let's make the states just a little bit bigger. So what I've got here is, as long as I see a 0 or 1, just go right through my string, right? But as soon as I see that space, go left. And then this loop is my, as long as I see a 1, replace it with a 0 and go left, right? Until, if I come to a lambda, then just write a 1 and stay put, because that's the first digit. On the other hand, if I see a 0, replace it with a 1, go left, and again, keep going left on 0s and 1s until I hit the beginning of the number, at which point I'll see a blank, and right, blank is the same as lambda, so then go right and halt. So let's see, let's just try this on a couple of examples, and then we'll test it on a bunch just to see what happens, right? So if I want a step, let's start by just adding, let's add 1 to the number 1, 1, right? So we're going to add 1 to 3, we should get 4. Okay, so I have my number 1, 1, and I'm going to step, right? I'm going to take a step. So I'm going all the way to the right till I find the end of my string, right? Keep going to the right. Now I see a space, so I should transition to Q1. Fantastic. Now I'm at Q1, and I see a 1, and this says if you see a 1, write a 0, go left, so I do that. If you see a 1, write a 0, go left. Let's do it again. Step. And now I see a blank, right? So I'm going to take my blank, replace it with a 1, and stay put. I got to halt, green light. My number is 100, 100 in base 2, right, which is 4 in base 10, and so I was adding a 1 to 1, 1, and I got 100, which is exactly what I expect to get in binary. Cool. Let me shrink this in slightly. It looks like when I'm doing the test, we do a step again, and we test it on, let's try it on a weird number now, 1011, that's not 1011, that's 10100, 111, 1011. Looks good. All right, and so we step, and we're going all the way to the right in Q0, right? And then we are going to, we see the blank, so we're going to go left. And we see a 1, so we'll loop, and we see a 1, we'll replace it with a 0 and loop like we did before. Oh, we see a 0, woohoo! We can turn that into a 1, and now all we need to do is go to the left until we see a space. As soon as we see the space, we go right and we halt. Magic, it worked. If we click on, trace, you have to click on one of the configurations, right? So we can see what happens. I'm going to click on that one, and I'll say trace, and it shows me my new number, right? What's left on the thing. So I added 1 to this number, and I got that. Looks pretty good, right? Of course, if my number, let's close this and just do one more. Let's add 1 to 4, so we get 5. If I input step and I say my input is 100, which is number 4, right? I'm going to stay in Q0 and move to the right. I see the space, I'm going to go left. Now I'm at Q1. I don't see any ones here, I just see a 0. So all I have to do, right, this is easy. I see a 0, replace it with a 1, go left. And then I'm going to keep going left till I get to the beginning of my string, go right, and woohoo, we win. So 1, 0, 0 plus 1 equals 1, 0, 1. And let's close that. The last thing I want to do now is just show you this really works. And so I don't know how to convince you better than to, let's do a multiple run, right? And let's make this a little bit bigger so you can see what we're going to do. Let's see what happens when we add it to 0. Oops, tab. And I'll add 1, tab, tab. And 1, 0, and 1, 1, and 1, 1, 1. Oops. Let's add 1, 0, 0 is the next number, right? That's 4, and 5, and 1, 1, 0. I keep tabbing, right? And 1, 1, 1 is 6. And what happens if we try 120, right? Theoretically, that shouldn't work. Let's make the table text size just a little bit smaller. Or we try adding it to 2. Shouldn't work, right? Okay. Or we try, well, that's good enough. Okay, let's run the inputs. And of course, all these guys are accepted, all these guys are rejected. How do we know what the total is? Well, let's click on 0 and say view trace, and it's up in the corner of my computer. But if I put it down here, look, 0 plus 1 is 1. Woohoo! And let's try 1 view trace. And 1 plus 1 is 2, 1, 0. Right? Isn't that great? It is kind of cool, right? Let's try 1, 1, 0, view trace. We got 1, 1, 1. And let's try 120 and view trace. And 120, it failed exactly where we thought it should on that too. So pretty cool. We've written a Turing machine that adds 1 to a number. That's something we couldn't do with those million more machines and stuff. One last thing, don't forget that you can label your states, and it might help you to label your states so that you have a better idea of what's going on. For example, I can take this state here. I'm in my attribute editor tool, and right click on it and say change label. And I could label this something like while, let's see, that doesn't say while, does it? So while, it's hard to type and dictate. While, let's see, if I have a 1 or a 0, you know, I'm kind of making up my own language here, go right. Okay, and there's while 1 or 0, go right, right? And, you know, it just might remind me what's going on here. Maybe that's not the best label for this. Maybe I should change the label to go right to end of string, right? Maybe that kind of explains what's going on more, right? And this one might be, I could add a label that says something like, you know, while I see ones, write 0 and carry the 1, right? It's kind of up to you what works and helps you, right? But whatever you can figure out that helps and helps you is great. One last thing, if you're in attribute editor mode and you right click here, you can hide the state labels and display them just by right clicking and then selecting this box. So if you don't see your labels when you make them, make sure you've got display state labels shown. So what if I want a Turing machine that adds 3 to a binary number? Well, that's pretty easy, really, right? I can just make a new Turing machine with building blocks. And let's put a new building block in here, which is my add 1. Right? Let's add 1. And we'll stick another one of them in there. Add 1, And we'll stick one last one in there, add one, okay. So we've got 3 of these add one blocks. And now let's just do the obvious, right? I'm going to make this an initial state. Better create a halt state. So I'm going to right click on Q3 and make it final, and let's change, oops, not the label, set the name to be halt, right? And let's think about what the transitions need to be between these. When I'm done, I'm pointing at the start of the string and I have either a 0 or 1, right? So I'm just going to stick a transition here that says if I stop and I stop at a 0, then leave it as a 0 and stay put. If I stop and I had a 1, leave it as a 1 and also stay put. That looks pretty good. And we'll do the same thing to get from our second adder here. If I see a 0, replace it with 0, stay put. If I see a 1, replace it with a 1 and stay put. And the same thing for leaving. If I see a 0, replace it with a 0 and stay put. If I see a 1, replace it with a 1 and stay put. And let's just try this on multiple run, right? So here is our table with lots of examples. Let me add in, you know, something like 100, 120, right? Or add in 856, just so we can see what happens. So if we run all these inputs, of course, all of these ones work and these 2 are rejected. And let's just see what happens. 1, 0, that's 2 plus 0 is 2, right? So we should expect that 2, and then if we add 3 to it, we should get 5. And 5 is 101 in binary. So let's click on this and let's view the trace. And like magic, 101. Or let's try seeing what happens if we, let's see, this is 7, right? So we have 10, which is 8 plus 2. So let's view the trace. And there we go. The 1s column, the 2s, the 4s, and the 8s. So 8 plus 2 is 10. Isn't that magic? It's really kind of cool. I mean, you know, on the one hand, you sort of knew it was going to work, right? Because you believe that functions work, right? You've been trained to do that in all the other courses you've taken. On the other hand, we just did that with a Turing machine, which is a crazy basic device. Of course, we can create infinite loops, programs that end up with infinite loops on our regular machines. And I said that Turing machines are equivalent to regular machines. So here's a program that has an infinite loop in it. This program is supposed to accept this language, A star C, A plus B plus C star. But it turns out that because of the way I intentionally made it to mess up, if it gets any strings in this language, it immediately goes into an infinite loop. So let's try it. Let's try a few strings in each of those languages. So let me move this a little bit closer so I can do a close-up. So let's do a test on, let's pick a couple things it accepts. So it accepts A, C. Let's try that one first. So we see an A, we just loop and go right. An A, go right, go right, go right, go right, go right. We see a C, we go right, we halt, and magic, we accepted. Because I didn't check to make sure that there's a blank space after that C, it could accept anything else in my alphabet, and that of course presumes that I didn't let anybody write anything besides A's, B's, and C's on my tape. If there's D's on my tape, it'll accept that too. But if we say try the string, I don't know, let's do 1A, a C, and then a bunch of A, B, A, C, C, A. And we step through. Oops, that was so fast. Let's reset. Let's do it again. I see the A, I go to the right. I see the C, oh, I'm leaving Q0, I'm going to halt. I accept, and whatever was on my string is still on my string. So let me show you an infinite loop. It's kind of cool. I mean, it's the way I designed it, right? If you see an A, write the A and go right. And if you see a B, write the B and go left. So for example, if I try the string, I don't know, a bunch of A's and then a bunch of B's. Starts out strong, it's doing the A thing and going right, that's fine. Doing the A thing and going right, that's fine. Now we see a B, oh, we go left. Now we see an A, oh, we go right. Left, right, left, right, left, right, left, right, left, right, right? I mean, it just keeps going and going and going. It's going to go as long as I keep clicking that button. Notice, of course, that if this were a building block, it would never leave, right? If it came up with this string. Cool, huh? Okay, a super quick thing to mention that you should know, but we're not going to study any of these things. The Turing machine that we use is equivalent to a Turing machine that has a tape that's only infinite in one direction. So our tape is infinite in both directions. It's equivalent to a Turing machine that is only infinite with a tape that's only infinite in one direction, right? It's also equivalent. That means you can't do any more or less with a Turing machine that has multiple heads, or a Turing machine that has multiple heads and multiple tapes, or in fact just multiple tapes and one head per tape. So the interesting thing is, even if you add more complexity to the kind of machine you use, you still end up with the same capabilities. Okay, let's go on to one last example. This is a Turing machine that accepts the language A to the N, B to the N, C to the N. This is an example that I got from JFLAP, from their website, but it's the classic example of a language that is not context-free, right? It's not context-free. It's not regular because it's not context-free, but a Turing machine can recognize it, right? A language where we have the same number of A's as B's as C's. So let me show you this mess. This is the Turing machine. And you can download this and try it. What I'm going to do is I'm going to give you a little bit of an overview of what's going on here. It's a mess, right? And then we'll do maybe one or two examples, and then we will call it a day. So here's what happens with this Turing machine. We start at state Q0. And what we're going to do is we're going to go through and we're going to start by looking for an A. And when we see an A, we're going to turn it into an X. We're going to kind of cross it out and go right. And then we're going to keep going right past all the A's we see and past any Y's. I'll tell you about Y in a minute, until we see a B. And when we see a B, we're going to turn it into a Y and then go right again. So those Y's that we went by were old B's that we've already matched to A's. So we find an A, we match it to a B, as it were, right? We turn that B to a Y. So we're kind of crossing off the B, crossing off the A. I've seen one A, I've seen one B. And then we zoom around in here. And as long as I see a B or a Z, right? Z is going to be what we're going to turn our C's into when we see them and use them up. We're going to come down here, and then I'm going to go back to the left and repeat. And I'm going to keep doing this, matching the A's to the B's to the C's until I'm done. And once I'm done all of that, I'm going to make sure, and that's what this loop piece does, make sure that I don't have any stray A's or B's or C's. Well, I guess we use up our A's, right? But no stray B's or C's lurking around, right? So actually, I think what I'm going to do is I'm going to leave you to try this one out yourselves and just to kind of see how it works and what happens, because it's going to be so tiny on my screen as to be almost impossible to really see what's going on. So give it a try yourself. I'll make sure that it's up on the class website, and it's also on the JFLAP website. You can find it there too. And give it a shot. It looks ever so slightly different than this on the JFLAP website. It just looks different because I moved this around a little bit so I could put my comments all over the place. Okay? So go play with Turing machines. They're super fun.